In our first examples, we're going to take a look at counting items that are not in a group. Remember, when you group things, you start talking about permutation and combination formulas. So that'll be in the next set of examples. So the first problem, we just have 6 people that are arranged in a row in a classroom. A classic demonstration to do live with people. If 6 people come in, the first person can sit down in 6 different desks. But once they sit down on those desks, the next person would have 5 desks to choose from, and then the next person would have 4, and then 3, and then 2, and then the last person only has 1 desk left. Now the problem is if you get all these people to stand back up and you tell this last person to choose, they then have 6 choices. So this is what's known as 6 factorial, which if you use a calculator, you're going to find the factorial button on a TI under Shift F2 or under Math and then scroll to prob. But if you have a Casio, you're going to want to look at the main menu and find it through there. Now, if you're using Desmos, you're going to want to go into the graphing calculator because most of statistics is done there, and there's actually within the keyboard an actual statistics feature under stats. But it doesn't have the factorial, ironically. If you use the scientific calculator, there's one in there, but it's sort of superfluous because you can just use Shift 1 on your keyboard and it'll do it for you. So as you can see, that's 720 both ways. So let's say you had 7 different pairs of shoes, right? And so if you arrange those 7 different pairs of shoes, you go into your closet and you want to wear a different pair every day. Well, the first day you have 7 choices. Once you choose that, you have 6 choices, and then so on. Okay, and again, once you get down to the end, let's say the next week after you finish this is actually quite a long time, but let's say you wanted to do that again, where your first choice could be it could go here. So this is what's known as 7 factorial, and you can type it all in, 7 times 6 times 5 times 4 times 3 times 2 times 1, or you could use the factorial button. And again, on Desmos, that is just going to be to use Shift 1 on your keyboard, the exclamation mark. All right, so looking at the next one, we have circular arrangements. Keep in mind that when you put things in an arrangement around a circle, a table, a tray, what have you, that these items are connected. Sorry to be a W there. So those items are connected, and if these items are connected, they actually share, like if you were to write them all out, these connections create repetitive values, which is taken care of by just subtracting 1 during this time when you have circular. So if you have 7 appetizers around a tray, that would reduce to 7 minus 1 factorial, which of course is 6 factorial. On the calculator, you get 720. 9 children sitting around a duck-duck-goose circle would become 9 minus 1 because they're sitting next to each other circularly, so that would be 8 factorial. So to look at those on Desmos, again, you would just go into Desmos and you would type, the first one is 6 factorial, which we already did in the previous example, but the other one is 8 factorial, and you find out there's 40,000 ways, 40,320 ways for students to sit in a duck-duck-goose circle of 9 children. It's kind of a phenomenal mathematical result when you really think about it. So what happens if you have identical items? Now keep in mind, when you have identical items, this is typically how the formula is written. Sometimes you'll see a ... here, meaning there can be more. Sometimes someone will put an S here and then a ... to indicate there's more. Just remember that you're taking the total number here and you're dividing by the product of the repetitive items. So what does that mean? Well, let's take a look at this problem. Anna is going to plant 11 colored flowers in her garden in her house, and she has red, yellow, and purple flowers. The question is, how many ways can she plant them? Or a better way to say this is, how many ways would there be, understanding that a red flower doesn't look any different from another red flower from a distance? Well, in her wheelbarrow, there are still 11 different potted flowers. But the red flowers from a distance are identical, so the one she pulled out first would not look any different than when she pulled out 3 flowers away. The 5 yellow flowers, same thing, so we would just have 5 repetitive yellow flowers. And the 2 purple flowers, you'd have the exact same idea. And so the problem comes out looking like this. Now, if you use a calculator like a TI, you would want to set this up in fraction mode, or else you'll have to put a parentheses here and here. Very important if you use an older calculator to use parentheses. If you have a newer calculator, there is a fraction mode in the TI under Alpha F1, and Casio has one as well on the face of the calculator. Again, but all this is just taken care of when you use Desmos because of the fact that you can just use the division button. So if you do 11 factorial and you highlight it, you could just hit divide or hit shift question mark to do backslash. And then you can just type these all in here, right, using or exclamation mark. You just type them all in here. You don't even need to say multiplies, okay? So 5 and then 2. And then you can see that it just looks exactly like you have it here. You don't have to put parentheses in Desmos as long as you use the division key by highlighting. It figures that out for you. Very useful. You don't even have to say multiply, but again, if you want to, you can see you get the same thing, but it's not necessary. See how it didn't change. Okay, so let's take a look at another classic example of this repetitive values that we see frequently on an SAT. So that is arranging letters and words. And I picked Alabama and Mississippi because of the fact that there's lots of repetitive letters, but I could have used algebra. Algebra has a lot of repetitive letters as well. And the way this works is you count the number of letters in the word. 1, 2, 3, 4, 5, 6, 7 letters in the word Alabama. And there are exactly 4, 1, 2, 3, 4 repetitive A's. And so that would just be, again, using the fraction button on the calculator. If you don't have a fraction button, you have to put this in parentheses every time. If you use Desmos, you would just come over here and say this is 7, and then this, of course, is just 4, and then it's done. 210 ways to write out the letters of Alabama. Now, Mississippi has more letters, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's 11 factorial. And again, think about it like this. If I were to take those letters and cut them up with scissors and put them in a bag, you'd have 11 letters sitting in that bag. However, you wouldn't be able to tell one of these I's from another I. They would look identical. So they would have 4 repetitive I's. And I would have 1, 2, 3, 4 repetitive S's. And then I would have 2 repetitive P's in that bag of letters, and I couldn't tell them apart. So on a TI, if you have a new one, Alpha F1, if you have a Casio, put it in fraction mode on the face of the calculator. If you have an older calculator, you'd want to use a parentheses. If you use Desmos, it sort of just takes care of itself. Keep in mind on the SOL, you will be given a SOL approved Virginia Desmos version. So it's just really a good idea to be using Desmos. So 34,650 ways to arrange the letters of Mississippi and 210 ways to arrange the letters of Alabama. Now, if you're wondering what the unit is on all of these, the unit is typically the word ways. Okay, so you just say this many ways, and it's the same thing for all of these, though most people don't make you include a unit. So this would be 720 ways. All right, let's look at our last example, which is what's known as repetitive, selection versus unrepetitive, which actually introduces permutation, believe it or not, which is kind of neat to talk about that. So in this first example, we have a 5-digit license plate, okay? Actually, looking at this, it says 7, so I'll change that to a 7. All right, that way I don't have to update the calculator. So we have 1, 2, 3, 4, 5, 6, 7 ways to make a license plate. Yeah, that makes sense because in Virginia there are 7 different ways to do that. And so if you are allowed to have repetitive English letters, there are 26 letters in the alphabet, so you can pick your first letter, A, and if you want to make the next letter A, you could choose through A through Z, all the way down the line here, okay? So all the way down the line, you would have 26 choices the whole time, okay? And that is just 26. If we multiply them all together, because you multiply to find this answer, it would just be raised to the 7th power, which is a pretty enormous number, right? And if I use Desmos, there's a nice little interesting difference. So if I say 26, to raise it to the power, you either use Shift 6 and put in to the 7th power here, or you can use the A to the B. Notice that Desmos puts it in scientific notation where the TI or possibly the Casio can actually handle writing all those out. This one you would have, just lop it off at 3 decimal places and say 10 to the 9th. So what happens if repetition is not allowed? So the same exact problem if I don't have repetition, 1, 2, 3, 4, 5, 6, 7. If I choose A, then the next set of letters, I can't choose A. So this would be 25. And then if I chose A and M, then I would only have 24 left, and then so on, 23, and then 22, and then 21, and then 20. And if you multiply all those together, you'll get this very large number. But this is actually the same thing as doing a permutation, because I'm taking 26 choices, and I'm making a selection of non-repetitive, right, of 7 of them. And if you go back and look at the definitions and terms, that's exactly what it says for this. You purposely arrange items where order matters. Think of a license plate like a password. And so you can actually use the permutation formula, and that explains what I was talking about here, where you have limited in factorial. So what is this talking about? Well, what it's talking about is like in this first example here, we had in factorial, but we went to 1. Same thing with this one, same thing with this one. But when I get down to here, when things are not allowed to repeat and I don't get down to 1, that is what a permutation is. So again, you can type it all out in the calculator if you want. So if I were to come up here and say 26, times, let me correct that first example, 26 times 25 times 24 times 23 times 22 times 21 times 20, I'll get this scientific notation number in the billions. Or I could use the factorial, which would be found under functions and stat. Keep in mind, if you do use the scientific, it's under functions miscellaneous, so just be careful. So we would come down here and we would do function stat, this choice. Now, you can't actually plug these in like you can on some newer TIs. You have to use this as if it's like Java, and this is the function you called, and you just have to say, this is the function I called. I want 26 choices. I'm selecting 7 of them. And so you can see that it gives me the exact same answer as I did when I just iterated it out. All right, so the last example is a kind of a fun one. So several years ago, Warren Buffett offered $1 billion if you could pick a perfect March Madness bracket. And the reason he did that is when you think about a basketball game, there are 2 choices that can happen. You can win or you can lose, which means each game has 2 choices. Game after game after game, you would have always 2 choices. And there was actually 63 games played in the March Madness tournament, which means that you would have 2 written out 63 times, or 2 to the 63rd power, which, as you can see, is a very large number. I mean, it's to the 18th in scientific notation. Of course, Desmos does a little bit better job at using scientific notation, in my opinion. So 2 to the 63rd, remember, to put the 63rd in, you use A to the B, or you use the caret button. That's 9.23 times 10 to the 18th. That is an enormous, almost incomprehensible number. So that's how many possible outcomes there were. That's how many brackets there would be. And so he felt very confident with this until a couple years later, somebody used a computer, and actually a computer could do that many if you had it set up fast enough to submit all those different brackets. And so he had to back off once computer speeds got a little faster. But when people were doing it by hand, that number is just too big to be able to determine. All right, so we looked at lots of examples that were just, non-grouped. And then when we looked at the idea that repetition was not being allowed, we started to introduce the idea of permutation. My advice is we'll do more permutations in the next video, but just go through each one of these again and think about lines, just go down the whole factorial, circular arrangements, make sure you understand the circular means subtract 1 from the total. Identical arrangements, make sure you divide by the product of those and use parentheses if you're using an older calculator. Taken care of if you just use Desmos. And then again, repetitive ones, just really focus on the 26 being multiplied repetitively and the 2 being multiplied repetitively. Don't worry about this example. It was really an introduction to the next video.